So the previous lectures had covered a variety of topics. One had looked at the history of light. One had looked at kind of sources of light, and I'd spoken about lasers and LEDs and lights of different varieties. The previous lecture was about absorption of light and the fact that things have colour because they have transitions within the molecule which match certain wavelengths. But it's not just absorption of light that gives me colour, but emission does as well. Now, a nice kind of overlap between where we finished and when we were talking about lights before is looking at corundrum lasers. So ruby lasers was the very first laser that was invented in 1960 by Meinman. And Ti sapphire lasers are incredibly common lasers today. They're just using a sapphire crystal or a corundrum crystal with titanium 3+ impurities. Both of these systems, you'll notice, have d electrons in them, and so the transition that's happening is between two d energy levels. And if you remember last time, I said that this was a forbidden transition. When we see it in absorption, the intensities of this absorption is very low, but in emission, I get a different effect. And the effect is because it's forbidden, I'm easily able to get that population inversion to allow me to have lasers. Now, this concept of emission is what most of my lecture today is going to be built on. So, here I have a ground state system. Both of my electrons are in the bottom. You'll notice I've labelled my orbitals differently here. I have orbitals labelled S and orbitals labelled T. Orbitals labelled S we refer to as singlets. This is because the electrons are paired, one up, one down. When the electrons are paired, if I have my spins of my electrons plus a half and minus a half, overall using this equation, big S is equal to 2s plus 1, plus a half minus a half is 0, so 2 times 0 is 0, plus 1 is 1, and S stands for singlet. My triplet state is where I have a half plus a half, then 2 times 1 is 2, plus 1 is 3. This is my triplet state. Now, triplets are lower in energy than the associated singlets, just the same reasons as Hund's rule. We know electrons like to be parallel if they can possibly be so. This is to reduce electronic repulsions, and so a triplet has a lower energy than the associated singlet state. There are various processes that go on within my molecule when I absorb light. I can go from the ground state singlet S0 and excite into the S1 level. This is the most common transition within a molecule. It is spin allowed, and we would just call this singlet-singlet absorption. Singlet-triplet absorption is very, very rare and consequently has a very, very low probability of happening and a very low intensity of colour. We would normally regard singlet-triplet absorption as not happening. If I have my excited state singlet, there are various things I can do with it. I can lose my energy as heat, vibrational relaxation. I can also lose my energy by giving out a photon of light, and we call this process fluorescence. This is the allowed transition of S1 to S0. The final one is the one I've actually labelled at the bottom in orange, and this is me converting my singlet state to a triplet state. This is called intersystem crossing, and ultimately will give out some heat as well. Now, if I have a triplet state, I have two possible pathways. I can lose the energy as light, and in this case we call it phosphorescence. Phosphorescence is the spin forbidden transition of losing the energy as light. Alternatively, I can lose the energy again by vibrational relaxation. Again, this is going to be a forbidden process because I have to change the spin of my electron. If I think about having a system where I have lots of excited states, this will decay using first order kinetics, and I just display a simple example of that here. So naturally, the A star excited state will decay to the A ground state. A first order process that means that every period of time if I lose half in the first period, I will lose half remaining in the second period. And so after 20 seconds, I lose half of what remains. And after 30 nanoseconds, I remove half again until I just keep on losing half. I can show this in terms of a quick plot of how much excited state remains, and we can see that this will fit to exactly the same kinetics as you're going to get out of any other first order process. Now, the lifetime, the length of time it takes for these processes to happen depends upon whether the transition is allowed or forbidden. Now, absorbance occurs on a very, very fast timescale, normally 10 to the minus 15 of a second, and vibrations within a molecule happen on hundreds of femtoseconds. The making and forming of bonds takes about 10 to the minus 12 seconds, or 1 picosecond. Now, fluorescence, which I said was our allowed transition, tends to have a lifetime in the nanoseconds, whereas phosphorescence can have a lifetime anywhere up to seconds. Now, we see this length of time as one being allowed and one being forbidden. Fluorescence, the allowed transition, happens very quickly. Phosphorescence, the forbidden transition, happens very, very slowly. If I look at fluorescence, I can see an interesting profile between what happens for absorption and what happens for the emission or fluorescence from a molecule. Here I show this molecule YoPro1 that just happens to be a yellow dye. On the left-hand side, I see its absorption spectrum, and the emission spectrum is shown on the right. You'll notice that these bands are almost perfectly symmetrical. They go around a middle, and they share the same shape. This process, where the spectra of the absorption and the emission are mirrored, is due to something called Stoke Shift. You'll notice that fluorescence occurs at longer wavelength. This would be lower energy. This is because we cannot create energy in our system, and it naturally will relax down to its lowest vibrational level of a given system. So this concept of Stoke Shift says that I take an excited state molecule and it has a different ground state structure to the ground state molecule. So if I follow this diagram from the bottom left, I have my molecule which is optimized for the ground state system. I absorb a photon of light into this, and I've said that this happens very quickly, 10 to the minus 15 of a second. This is 1,000 times faster than the molecule has chance to reorganize and vibrate. Consequently, when I excite into a non-optimized excited state. Given a few picoseconds, this can then relax into an optimized excited state. But as I optimize the excited state, I de-optimize the ground state. When light is given out, it now has a lower energy gap or longer wavelength than when light is absorbed. Ultimately, the actual process of losing the photon only takes, again, somewhere in the femtosecond regime. And so the molecule does not have a chance to reorganize then either. I will keep on going around this system, seeing a different energy profile for the absorption and the emission, and this is why the two spectra appear to be mirror images of each other. Now, emission of light is a really important thing, and because of this difference in energy, I can actually make light that I can't see, UV light, into light that I can. This change in wavelength of light is basically the origin of something that we call optical brighteners. Now, once upon a time, optical brighteners weren't quite what they are today. What they used to do is be a very pale blue dye, and that blue dye would offset any yellow colour in white fabrics. This blue dye was a fool for the eye, but it didn't do anything other than kind of offset the yellow colour. Now fluorescent molecules are added instead. These molecules take light that we can't see, UV light, and due to this Stoke shift, this kind of downplay of energy, they turn it into light that we can, blue light. This blue light helps to offset any slight yellow colour within our whites. Optical brighteners are a massively important area in the domestic chemistry regime, and huge amounts of money have been spent on making things that make our whites better and better. It used to be that DAS was the thing that you bought for whiter than white whites, but now we have Vanish and Vanish Gold and Vanish White, and any number of things that will advertise as getting our clothes being brighter than white or kind of best colour ever. Emission's also useful if we think about being able to look at things. This is a series of DNA. I've gone from 3 different types here. One is this supercoiled shape, one is linear, and one is open circle. The idea is that we can't actually see the DNA. It's colourless to our eyes, but I can use a fluorescent molecule so that I can see it. These fluorescent molecules are so sensitive that whilst on the left-hand side we can see many, many molecules together, on the right-hand side this is a picture of a single molecule of DNA relaxing, observed using one of these fluorescent dyes. The fluorescent dye in question is actually this YoPro1 I showed you the spectra of before. In this case we're using a quirk of its structure in order to see this fluorescence enhancement when binding to DNA. I show the emission spectra of YoPro1 in pink when it's bound to DNA and in blue when it's a free dye. The difference in lifetime, and therefore the difference in intensity of signal that we see, is caused by a restriction of rotation around the middle of this molecule. When the molecule is free to rotate, it can lose its energy by vibrations. When I remove this ability, it no longer can lose the energy in such an easy fashion, and so it's more likely to give out light and fluoresce. There are various ways that we can use molecules to look at DNA, but essentially we're making the use of the fact that DNA has different ways that we can bind molecules to it. DNA itself is essentially a ladder of base pairs. It has a negatively charged backbone, and so I can make the most of any cationic interactions. The dye molecules can sit either between the base pairs or in the groove and restrict rotation this way. Sometimes molecules can even sit externally, but these are usually less good at showing any enhancement of emission. There are a large number of DNA stains nowadays, and ultimately it's made working with DNA a lot safer, because it used to be that all DNA was labelled with radioactive molecules. So another place where we use a molecular transition or rotation of a bond is actually in how we see. The protein rhodopsin has a molecule called retinal, which is bound into the protein. This molecule has a simple rotation, a simple cis-trans isomerization, which is the basis of all vision. It is nothing more than the fact that when we excite a molecule, we allow a rotation around a bond which previously was not available. This conjugated system is rigid unless a photon of light is absorbed. Another possibility of using light is to use light to actually treat cancers or other places where we want to destroy cells, perhaps in sterilization of blood or in sterilization of materials. Essentially, the whole basis of it is a molecule absorbed light, and it will generate something which can then go on and react with the DNA or other pathogens. Photodynamic therapy is still a young science for things like anti-cancer or sterilization, but it's been well used in America for a long time in cleaning the pool, where the dimethylene blue was quite literally thrown in and the sun allowed to do its job. Photodynamic therapy has also been used in treating acne, and more recently has been used in field trials to sterilize blood that is donated from one person ready for being received into another. For me, one of the coolest things about light, though, is being able to pick up tiny objects like cells just using a beam of light. Now this is using the same principles we have with rainbows, refraction of light, but it's also looking at the fact that momentum has to be conserved. If a beam of light is changing direction, I can consider it as a photon. If the photon is changing direction, then there must be a change of momentum. This basic principle is actually a really useful tool. So for example, if I introduce a laser beam, I can move it and manage to pick up my molecule. My molecule will actually be drawn into this laser beam. And now, wherever I move my laser beam, my molecule will follow. This remarkable property of light has actually helped revolutionize what we're able to do in terms of picking up and moving tiny things in nanotechnology. I hope that this lecture has kind of given you some ideas of the uses of light and also emission of light. I could talk about this stuff for absolutely ages. There's more to do with light than I could possibly mention in 4 lectures. But hopefully it will give you an idea of just some of the interesting things. Really, I don't mind what you learn here. I just want you to look at the world around you and the colour and the beauty of it all in a new way.